Welcome, everyone. We will get started in just a moment. Let's get folks a minute or two to join. Please note that this section is being recorded. While we wait, feel free to check your audio and video settings. All right, let's go ahead and get started. Good morning, good afternoon, or good evening, depending on where you are joining us from today. Welcome to this IEEE course-wide webinar. My name is Chao Fang, a postdoctoral researcher at KU Leuven, Belgium, and I will be your moderator today. Before we begin, please allow me to take a moment to introduce the platform that makes our event possible. This webinar is organized under the IEEE Circuits and Systems Society Institute for Global Education, or IGE. Its mission is straightforward: to become the go-to resource for learners at all levels, from students and young professionals to seasoned practitioners and educators across all fields of the interest within CAS. CAS IGE offers a rich portfolio of educational programs in 2026, including distinguished lecture programs, seasonal schools, webinars like today's, and much more. Participants can also earn digital baggage shareable on LinkedIn, PDH CEU educational credits, or certificates of completion. There is truly something for everyone at every stage of your career. If you are not yet a CAS member or would like to learn more or get involved, I highly encourage you to visit ieecas.org or reach out directly to the CAS operations managers at manager@ieecas.org. And now let me turn to today's talk, Demystifying the Black Art towards a new paradigm for semantic analog IC design. Analog IC design has long been regarded as a craft mastered only through years of experience. Today's speaker is working to change that. Professor Hesham Omran received his PhD in electrical engineering from KAUST in 2015 and is currently an associate professor at Integrated Circuits Lab, Ain Shams University, Cairo, Egypt. He co-founded Master Micro in 2020 to develop the Analog Designer's Toolbox, a novel EDA tool redefining the paradigm for analog IC design. He has published over 50 papers in international journals and conferences and has received several prestigious awards, including the DEC Innovators Award in 2022 and the UNESCO Offering Award for Young Scientists in STEAM in 2023. It's a real pleasure to have him with us today. Please join me in giving a warm welcome to Professor Hesham Omran.
So thank you, Dr. Chow, for the introduction, and thank you everyone for being here. Let me share my screen. Okay. So thank you again for being here today, and I'm glad to be with you to talk about a new paradigm for systematic analog IC design. As Dr. Chow mentioned, I am based in Cairo, Egypt. And when you think of Egypt, probably the first two things that go straight to your mind are the pyramids and the Nile River. But what many people do not know is that Egypt is also a hub for a thriving semiconductor industry. We have many multinational semiconductor companies like MediaTek, Analog Devices, Synopsys, and Global Foundries. And we have also local IC design companies all of them working in several domains like analog RF design, digital design and verification, EDA tool development, and much more. So it is not just about history and it is not just about the Nile River. And when I talk about semiconductors and electronics, I always like to start with this picture of ENIAC, the first general purpose electronic computer. And the reason I like to show this picture is that when you compare it with the smartphone that everyone now carries in his pocket, you feel how much tremendous change has happened in the field of electronics in the last 80 years. And this change has changed almost everything in our life. It has changed the way we communicate, the way we work, the way we play, the way we travel. Everything has changed due to electronics. And all of this is based on these magic black squares, the integrated circuits or the semiconductor chips. And inside every integrated circuits, we have billions of transistors, a tremendous number of transistors, and each transistor has dimensions in the order of nanometers. And when we think about this huge number of transistors, we can say that they perform two main functions, analog functions and digital functions. As we know, analog is continuous in time, continuous in amplitude, and digital is discrete in time and discrete in amplitude. When we think from the perspective of the transistor count, we find that actually the majority of this large number of transistors is performing digital functions. So digital transistors or transistors that perform digital functions are the majority in our IC, in our integrated circuits. But it is surprising to know that from the perspective of design time and design effort, the small fraction of transistors that are performing analog functions are actually the bottleneck. They are the bottleneck in terms of design time and in terms of design effort. And one main reason for this is that digital design is highly automated. The designers actually work at higher levels of abstraction. They use code to describe their designs, and then EDA tools translate this code to schematics and to layouts. But analog designers are still working at the transistor level. They need to define their transistor geometry at the schematic level, and they need to draw these transistors manually at the layout level. So this is one main reason why analog design is the bottleneck in terms of design time and in terms of design effort. And if you are not very familiar about analog design, you may ask, so why do we care about analog design? So everyone now is talking about digital chips, GPUs, CPUs. So why do we really care about analog design? And the answer is simple, because we live in an analog world. The physical world and all the physical signals around us are actually analog signals. Whether you talk about or think about voice, light, electromagnetic waves, temperature, pressure, voltage, everything is analog. So we need some sort of interface to connect between the physical world, the analog world, and the virtual digital world, the virtual processors and the memories, digital memories. We need an interface to connect these worlds. And this interface must be designed by analog IC designers. They are the ones who connect the physical world to the digital world. And actually, even the power and the clock signals that the digital world rely on are generated by analog blocks and by analog designers. So we will always need analog design and we will always need analog designers. And to give you a clear example, everyone now is talking about artificial intelligence and AI, and we know that all the AI revolution is powered by data centers. These are the new factories in the AI era. And inside these data centers, we have thousands of servers, and each server has lots of GPUs and CPUs. And again, you may think that all of this is just digital chips, digital GPUs and digital CPUs. But what we need to do is to connect these servers together. And this connection can be in the form of cables, copper cables or optical fiber cables. And when the signal travels across the cable, then this is an analog signal traveling in the physical world. So we need an analog transmitter and an analog receiver in order to connect these servers together. So analog design is always needed even in the AI era. So now let's talk back about this bottleneck in the design time and in the design effort. And you may be surprised to know that since the release of Berkeley Spice in the 1970s, and Berkeley Spice is the most famous analog simulation tool, there has been no major change in the analog design flow. We have been almost designing our analog circuits in the same way. And actually, with the new technology node and the nanometer transistors, things are becoming worse because there is a big gap between the hand analysis that you can do with the simple analytical equations and the real simulation results that you get when you simulate your circuit using the modern simulation models. And we can say that we have a big problem in analog IC design because the process, as I mentioned, is a manual process, iterative process. It is dependent on experts. You need lots of experience to design an analog block, and it is non-systematic flow. It is very difficult to teach or to document the way the analog designer thinks and the way the analog designer works. And even for an expert, the design point that he eventually gets may be a suboptimal design point. You may be wasting lots of area or lots of power or lots of performance, and things are getting worse with the increasing technology complexity. So, how are the analog designers handling all these problems, or what are the methodologies that are used by analog designers nowadays? The first one and the funniest one is the Spice Monkey design methodology. And I'm borrowing this name from Professor Boris Merman, who actually made this name famous. And the Spice Monkey design methodology is about iterating on spice, just trying more values for your transistor geometry, doing sweeps, till somehow you get a working circuit. You don't know how it works, you don't know why it works, you just get a simulation result that is matching the specs you are looking for. And one of the worst things about this methodology is that if you have any change in the specs or any change in the technology, you have to repeat all this nightmare again. You have to repeat all these sweeps. And of course, this is always a suboptimal design methodology, and it is not a scientific or a systematic design methodology. The second one is what I call the novice designer methodology. In this methodology, you start with the simple analytical equations like the square law, which you can find in the analog IC design textbooks. You spend some time trying to characterize your technology to get the process constants like the mobility and the Cox, and then you do your hand analysis, get the sizing for your transistors. But the surprise is when you simulate your circuit using SPICE or any other simulation tool, you will find that the simulation results are far away from your analytical expectations. And again, one main reason is that the simple models that you use are not really matching the actual transistor models that are used by the simulator. So eventually you will throw away your hand analysis and you will revert back to the Spice Monkey design methodology. At least you will have some design charts and you will have some simulation results to show in your report or in your design review. And again, of course, this is not a good design methodology. The third one, which I call the serious designer methodology, and actually it is the one used by professional and expert analog designers, is that you spend some time to characterize your technology. And then you store the technology characteristics in the form of lookup tables or in the form of design charts. Some designers like to use MATLAB and others like to use Excel. And then you use these transistor parameters in order to find the sizing of the transistors. Again, you are now using the simulation results that are generated from the simulator itself. So you are avoiding the simple models problem. You're avoiding the errors of the simplified analytical equations. But of course, It is a manual process, non-systematic process, and you need to go back and forth between different tools in order to design your circuit. But of course, it is much better than the previous two design methodologies. So my goal today is to show how actually we can generalize this methodology and make it a systematic and a professional design methodology that can be applied at the transistor level and also at the circuit level. And all of this relies on pre-computed lookup tables. Pre-computed lookup tables means that we will use the device models that are shipped by the fab in the PDK, and we will use the standard simulator to pre-compute the device properties. And this is done only once for a given technology, and the results are stored in data structures, which we call lookup tables. And these lookup tables abstract the nonlinear behavior of the device. So it captures the real behavior of the device. It captures all the details of the complex simulation models, but in the form of data. And then these lookup tables can be used as a bridge between the designer and the simulation. So instead of doing lots of iterations on the simulation tools in a Spice Monkey design paradigm, you can actually use the data in these lookup tables to visualize the design space, optimize your circuit so that when you go to the simulator, you go with an optimal design point. And this is risk-free because, again, you are using data generated from the simulator, and eventually you are verifying your circuit back using your standard simulator. So it is an extra step in the design process, but this extra step helps you to make that design process an optimized and a systematic one. And when you build these lookup tables, it is very important to differentiate between the OP parameters, the operating point parameters, and the effective parameters of the transistors. When we run operating point simulations, we get the parameters of the intrinsic device. The intrinsic device has some GM, capacitance, GDS, the electrical parameters that we all know, but the problem is it is not just about the intrinsic device. The intrinsic device may have lots of parasitic elements like resistors, capacitors, diodes, and actually in the FinFET technologies, the devices are built by stacking several transistors in series. And what we really care about is the terminal behavior of the device. So if I think of this device with all its parasitics, or if I think about this composite device, what I really need to care about is the effective parameters. What is the effective GM? What is the effective capacitance? What is the effective GDS? And so on. What's the effective mismatch? And so on. And to characterize these effective parameters, we use what we call the black box characterization. We deal with the device as a black box, and this black box can contain the device, its parasitics. You can actually use the post-layout extracted view of the device, and then you characterize the device in the form of Y parameters matrix. And using this Y parameters matrix, you can actually compute any electrical parameter of the device. You can compute the effective GM, effective capacitance, effective GDS, and so on. So you get that terminal to terminal effective and actual behavior of your composite device, and eventually this is the real behavior that is going to affect your circuit when this device is placed in an actual circuit. So let's now see how we can apply this and use this lookup table data in order to make the design process a systematic one at the device level and also at the circuit level. So let's talk back about the device sizing process. When we use schematic viewers to connect and size our circuit, what we can control is the geometry. You can select any device in your schematic, and then you can change the geometry properties of this device. You can change the width, the number of fingers, the channel length, and so on. And again, this is a 50-year-old time-consuming, non-intuitive process. Why? Because you actually need to run your SPICE simulation in order to get the electrical parameters of the device. The electrical parameters are the real parameters that we care about as designers. You need to run your SPICE simulation in order to get your GM, your GM over ID, the gain, the FT, the noise, the mismatch, and so on. And this doesn't make sense. It doesn't make sense to start with what you don't know, and then you need to run several simulations in order to find what you really need and what you really care about. And using the lookup tables, you can actually flip this design process. You can start with the electrical parameters as inputs, and then the sizing process is simply a search process that can be done in milliseconds. So you can find the equivalent geometry that satisfies the electrical parameters that you are looking for. So this can be very fast, it can be accurate because again, it is based on the lookup tables that were generated using your standard simulator and your standard simulation models. And it is also intuitive because you actually start with what you really care about. You start with the real electrical parameters that affect your circuit behavior. And the good news is that this can also be integrated into the schematic editors that we use. So this is an example of how you can use this methodology. So here, as you can see, I'm not controlling the geometry. I'm actually controlling the electrical parameters. For example, I define my device using its bias current, its GM over ID, its intrinsic gain. So these are the electrical parameters of the device. And in the background, instantly, we can search for the equivalent sizing, the equivalent channel length, and the equivalent width, and we can see all the properties of the device. And once you are satisfied with the electrical parameters and the sizing that you get, you can directly apply this to the devices in the schematic. So the sizing process becomes a systematic process. You tune the electrical parameters that you care about. You can select any electrical parameter and use it to search your lookup table. You can view the results instantly without a run button, without running a simulation in the background. And then you can simply select the devices in the schematic and apply your sizing. And the good thing is that you can also generalize this to sweeps. It is not just about single point design of transistor. You can also do electrical parameters sweeps. So what I can sweep is anything, not just the width, not just the length, not just the terminal voltage. I can sweep the electrical parameters. So here, for example, I define my GM over ID as the sweep variable, and I define my intrinsic gain as the parametric sweep variable. And as you can see here, the sizing becomes an output of the process, not an input to the process. And this makes sense because I don't know the sizing. I need actually a tool to help me find the sizing that satisfies the electrical parameters I'm looking for. So here I get my sizing as the output variable. I can see for a given GM over ID, for a given intrinsic gain, what is the corresponding channel length, what is the corresponding channel width. So the electrical parameters becomes your tuning and your sweep variable. It becomes your parametric sweep variable. And again, you can control this the way you want. You can sweep the FT, you can sweep the capacitance, you can sweep the mismatch, you can sweep any electrical parameter that affects your circuit behavior. So let's take an example for a digital circuit, like an inverter. For a digital circuit like this, sometimes we want to design it for equal rise and fall times. And the conventional way of doing this is that you need to set up a transient simulation, and you need to set up a parametric sweep, repeat this transient simulation several times in order to find the sizing parameters that will give you equal rise and fall times. But when you think about sizing using lookup tables, you can simply design these two transistors such that they drive the same on current. If you drive the same on current in the same capacitance, you end up with the same delay. So if I size this NMOS device and this PMOS device to drive the same on current, I can actually get the same rise and fall times in a single step. And this is a systematic way of doing it without running SPICE in the background, without doing a parametric sweep, without running multiple transient simulations. The sizing process can be turned into a one-step process that uses the lookup tables without running the simulation in the background. So to summarize this part, the old way of doing device sizing is controlling the geometry. And again, you start with the unknown and then do trial and error, many simulations to find the electrical parameters that you need. And the modern way that is powered by pre-computed lookup tables is that you start with the electrical parameters. You start with what you care about, and the geometry of the transistor becomes an output to the sizing process instead of being an input to the sizing process. So all of this, we are talking about device level sizing. So what if we are uh, talking about a complete circuit? If I want to size a circuit as a whole without sizing the individual transistors one by one, again, the conventional way of sizing a complete circuit is that you draw the schematic of your circuit, you set up a test bench, and then you use SPICE simulator that uses maybe BC models in order to solve your circuit, find the specs. Like, for example, for an amplifier circuit, you may care about the gain, the bandwidth, the power consumption, and so on. And if the specs here are not matching what you are looking for, you need to tune your transistors back, run the simulation again in a manual, iterative, time-consuming, suboptimal process. So how can we fix actually this old, inefficient way? You know that SPICE is a generic solver. It's a solver that can solve any circuit. And again, it takes time to solve the complicated transistor models. And if you have lookup tables, pre-computed lookup tables for your devices, you already have the data that describes the device behavior. And instead of using a generic solver, what you can do is you can compile a custom solver for your circuit. This custom solver is a solver that has been optimized to solve a specific circuit in a vectorized way, which means it can handle hundreds of thousands of design points simultaneously so that it can help you paint the design space. You can visualize the design space. And because this uses the lookup tables that were generated using your simulator and your device models, you maintain the accuracy. It is very fast because it doesn't call SPICE in the loop. You don't have a SPICE in the loop. And it is intuitive because it can help you see the design space. It can help you feel the different trade-offs in your design parameters. So the design process becomes like building a library. You have your design, you export it and compile a custom solver for this design. And then once you have this custom solver, you can generate the design space to optimize your circuit across process voltage and temperature. You can redesign it for different specs or redesign it for a different technology. And at the end of the day, you can send it back to your standard schematic editor, standard simulator, so that you can verify your operation. And the way you can visualize this design space can be also innovative. Like, for example, you can visualize the design space in the form of sliders. These sliders show you what is the feasibility range of your circuit. And when you apply a constraint, like here, for example, I'm applying a constraint on the loop gain, you can see how this constraint is affecting all other circuit specs. So you can examine as many what if scenarios as you want. And again, this is not just equations, this uses the actual numerical behavior of your transistor, and it changes, of course, from one technology to another, from one device type to another. So you are capturing the real behavior of the circuit. So here, for example, I'm applying a constraint on my phase margin, and I can see how this constraint is affecting my power consumption. You can again see the interaction between different specs, the interaction between the specs of the circuit and the design variables. All of this can be visualized, all of this can be examined in an interactive way. So this can help you relate the design variables to the specs and understand the trade-offs between the design variables and understand the feasibility limits of your circuit. So let's see an example to see how this works. Let's assume we want to design a capacitive feedback amplifier. This is a circuit that is used in many analog systems like analog to digital converters and analog filters. And let's assume that we want to minimize the power consumption and we want to minimize the noise. But we want to minimize these two parameters while satisfying other constraints. We want to satisfy some DC loop gain to control the static error. We want to satisfy some bandwidth, which again affects your settling time. And the phase margin, of course, is your closed loop stability. So if you go to an expert designer, he may propose that you use a folded cascade topology for your amplifier, and he can give you some directions on how to size your circuit. But of course, it is very difficult or even impossible to give numerical values for the sizes of the transistors, because these numerical values will differ from one technology to another. And if you change one of these specs, if I change, for example, the loop gain or the bandwidth, I will need a completely different set of geometries or a completely different set of numerical variables. But when you use the design space painting or the design space exploration methodology, you can actually visualize the design space in a matter of seconds. So you can see what is the feasibility limit of your circuit. For example, the blue points here represent the full design space. And when I apply my constraints, here I apply a constraint on the loop gain, a constraint on the bandwidth, a constraint on the phase margin, I can see this orange island, and this orange island represents the design points that satisfy my constraints. And here I can directly see what is the minimum power, for example, what is the minimum bias current that can give me the constraints I'm looking for. Here I can see what is the bias point, for example, that I should use for the input pair, what GM over ID should I use to bias the input pair in order to minimize the power consumption. And here I can see how the power consumption and the noise actually are traded off versus each other. This is the Pareto optimal front that actually minimizes the power and the noise. And you need to move along this Pareto optimal front in order to optimize the power and optimize the noise. And using this design space and these numerical solutions, you can also do interactive sensitivity analysis. So for example, you can see for a given spec, let's say the loop gain, what parameters do I need to tune and which transistors do I need to tune and in which direction. So the green color here means directly correlated, the red color means inversely correlated, and the yellow color means uncorrelated. So if I need to tune up the bandwidth, I need to tune up the GM over ID of the input pair, I need to tune up my bias current, I need to tune down this device M4 here. This is the PMOS device adding lots of parasitics at the output, so you need to decrease, for example, the GM over ID of this device in order to decrease the parasitics that are at the output node. So using this interactive sensitivity analysis, it can be a teaching method actually to help you learn about your circuit, feel what are the parameters that affect every spec. And it can also be used as a bridge between the hand analysis and the actual simulation results. So this can help you build a bridge across the gap that we talked about in the beginning of the lecture, so that you connect your hand analysis to the real numerical results in an interactive way, again, that uses the lookup tables in the background to give you instant results without running the simulation in the background. And if you perform optimization using any optimization method like the genetic algorithm or whatever optimization method you like, the unique thing here is that you can see how the optimized points actually appear in the design space. So this is again the design space of the power versus the noise. And if you don't see this design space, you can end up with a design point located here. Remember that this orange island already satisfies the specs I am looking for. So I can end up with a design point located here, and it is giving me all the specs that I'm looking for, but I'm spending maybe 3 times more than the minimum power consumption. And you don't know that your design point is a bad design point because you don't see this design space. But once you see this design space, you can quickly identify that a design point located here will be an inferior design point. And you need to move to the Pareto optimal front here in order to get the best power or the best noise. So I can use a design point here if I want to minimize the power and sacrifice the noise, or I can move along this direction if I want to minimize the noise, but spend a bit extra power consumption. So once you can paint the design space, you can now make informed design decisions. You can now make good judgments about the quality of your design and whether there is room for optimization or you already have the best possible design point. And the last thing that you need to do is to make sure that actually the results you are getting from the lookup tables are matching actually the actual simulation results. And in this case, this comparison can be done automatically by invoking the simulator in the background. And again, this is the only step where you need to invoke your simulator, and then you can get a comparison between what you have from the lookup tables and what you have from your simulator, so that you make sure that the results you are getting from the lookup tables are really matching the simulation results that you will have when you export your circuit back to your schematic editor. Another thing that you can do by using the design space exploration and the lookup tables is that you can make a good and informed topology choice. So if you have a set of specifications and you want to select a topology for your circuit, like if you design an amplifier, a classical question is, should I use a cascode or should I just use a simple amplifier? And of course, we know that one of the main things that affect this decision is the DC gain and the output swing. So you have many values for DC gain and many values for output swing depending on how you are going to size your circuit. But if you use the design space exploration to paint your design space, I can quickly actually see where the simple circuit will work, which is the orange island here, and where the cascode will work, which is the blue island here. So you can see which circuit best matches the specs you are looking for. And of course, this design space will differ from one technology to another because the transistor parameters will be different. You will get different intrinsic gain depending on the technology. You will get different output swing depending on the supply and the technology. So these comparisons, again, will be dependent on the technology that you choose, the device flavors that you choose. It is actual numerical comparison, not just a theoretical comparison using design equations. In addition to using these scatter plots to do the comparisons, you can also use the interactive sliders to see the comparison. For example, this is a comparison between a telescopic cascode and a folded cascode. Number one here is telescopic. You can see telescopic can give you much higher gain, much higher bandwidth, much higher unity gain frequency. But the folded cascode has the unique advantage of the flexible common mode input range. So you can quickly identify that if you want to use, for example, a common mode input near 0 voltage, then the telescopic cascode will not work, and the folded cascode will be the only choice that helps you in the design you are looking for. So you can make this comparison to learn about different circuit topologies, how they compare against each other, and what is the best topology for the specs you are looking for. And of course, one main concern when you use the lookup tables will be the accuracy. So if I use a specific step in order to build my table, so how much accuracy can I get? And we actually published a paper about using the lookup tables to design sensitive circuits like the band gap circuit. And you can see here, this is the output voltage of the band gap circuit, and you can see the change here is in the order of just a few millivolts. And the blue lines are the results from the simulation, and the red circles are the results from synthesis using the lookup tables. And by using smart interpolation methods, you can actually get quite good accuracy with quite small errors that can help you to design sensitive circuit like the band gap circuits. And this is also the mismatch of the output voltage, and again the blue line from the simulation very well matches the red line from the synthesis. So you can use the lookup tables in sensitive circuits, and you can use the lookup tables to get very small interpolation errors, as long as you are generating a good data set and you are using a good interpolation method to connect the dots between your data set points. Another thing that you can use using the lookup table methodology is when you do design migration. Design migration means I want to port or migrate my design from one technology to another technology. And a big challenge is how to size actually the new design. Should I keep the same sizing or should I resize my circuit? And if you handle the circuit as a whole, this becomes a very difficult and a challenging problem if you have a big hierarchical design. But using the lookup tables, you can actually use the electrical parameters as inputs as we have explained. So you can work your circuit device by device and use the lookup tables of the target technology to find the equivalent sizing that gives you the same electrical properties for every device to match your reference design. And in this case, you can migrate your design while maintaining the electrical properties of your devices without having to run spice-based optimization on a big hierarchical design, which can take several days. Because you are now working device by device, you are using the lookup tables to get the electrical properties without running the simulation in the background. So now let's conclude our talk using pre-computed lookup tables and custom compiled solvers. You can design analog circuits in a new paradigm. You can design analog circuits in a new way that can give you advantages that was not there actually using the classical design methods. You can get time savings. You can build analog blocks in minutes instead of days. You can get truly global optimal results because you can paint and see the design space. You can get the best power possible, best performance, best area. You can gain design insights by understanding the trade-offs, understanding the feasibility limits of your circuit, and most importantly, the whole analog design process is not a black art anymore. You can make it a well-defined systematic process, a process that can be documented, a process that can be taught from senior generations of designers to junior generations of designers, a process that can be intuitive and understandable. So thank you very much for your attention.
Okay. Thank you so much for your excellent presentation, Hesham. Now it's the QA section. Let's see if our attendants have some questions would like to interact with our speakers. And you can unmute your voice or you can also type in the webinar chat.
So I can see the first question. It is asking about whether this is the same approach that is promoted by Professor Boris Merman. It is actually an extension of the approach that was promoted by Professor Boris Merman. I co-authored a couple of papers with Professor Merman on using the lookup tables for systematic design. And then we took this one step further by developing a complete tool that uses the lookup tables in order to size transistors again at the device level or at the circuit level. So yes, it is an extension of Professor Merman's work. So there is another question about using the lookup tables for analog and RF design. Yes, you can use, of course, the lookup tables for analog and RF design. Of course, the parameters that you care about will be different. For analog design, you may care more about, for example, the mismatch or the intrinsic gain and so on. For RF design, you will care more about the parasitics, the capacitances, the FT, and so on. But the approach can be used for different types of circuits. So there is another question about the scope of this approach. So we can use it definitely for linear blocks like amplifiers, current mirrors, LDOs, and so on. But what about nonlinear circuits? Can we use this approach for nonlinear circuits? This is a good question. To use this approach for nonlinear circuits, you can size individual devices like what I have explained in the sizing assistant methodology here. So you can size individual devices, you can choose the electrical parameters of individual devices, or you can use approximate equations to describe your nonlinear circuit. The problem for nonlinear circuits is that you cannot build a custom solver for nonlinear circuits in an easy way. So the approach that you build a custom solver that can handle millions of design points, this approach is applicable for linear circuits. But for nonlinear circuits where you need to run transient simulations, it is almost impossible to run transient simulations for millions of design points, because the transient simulation itself is not a single simulation. It's actually thousands or even more of simulation design points, because you solve your circuit at each time step. So if you can actually get design equations for your circuit and then use the lookup tables to plug in the primitive parameters of the transistors into the design equations, then you can generalize this to nonlinear circuits. But of course, it is not going to be as automated and as straightforward as it can be done for linear circuits. So there is another question about supporting types of devices like gallium nitride and supporting generic circuits. So you can characterize any device that is defined by terminal voltages. So if your device is four terminal device, you can have more terminals, but these additional terminals will be kept at fixed bias voltages. So if you have a device that can be characterized by four terminals, then yes, you can characterize it and you can use the same methodology. And whether you can add or use generic circuits, the answer is yes, as long as these generic circuits are linear circuits. So if they are linear circuits, you can export your design from your schematic editor. You can compile a custom solver for your design that uses the lookup tables, and you will have your custom solver that can generate the design space, paint the design space, and so on. So there's also a question about fabricating designs that showed better performance with ADT. So the goal of ADT is not to beat the simulator. So again, at the end of the day, you will use your standard simulator to verify your circuit before doing the tape out. So your fabrication results, when you compare them, you will actually compare them versus your simulation results, which means that if your models are good, the simulation results will match the fabrication results. If your models are bad, then it doesn't matter whether you use SPICE, whether you use ADT or any other tool, your fabrication results will be quite different from your simulation results. So the goal is not to beat the simulator, the goal is to paint the design space in order to help you go to the simulation step with the optimal design point, instead of just doing trial and error in a lengthy iterative process using standard SPICE simulation. So there is also a question about using the lookup tables in industrial solutions. If you mean you can use generate the lookup tables for commercial PDKs, then yes, you can definitely do this. There are several approaches to do this. One of them is using ADT, the Analog Designers Toolbox, which can handle different types of PDKs from different fabs. It can help you generate these lookup tables and integrate the sizing methodology with your standard, for example, schematic editor or standard simulator and so on. So there is another question about should actually we forget about SPICE and just work with lookup table tools? The answer is definitely no. As I mentioned, the lookup table based tools are a bridge. The aim is to actually build a bridge that addresses the gap that was there between the hand analysis and the SPICE based tools. And this bridge is the lookup table based tools. And the goal is, again, to avoid lengthy iterations on the simulation tools. At the end of the day, you will verify your circuit using a simulation tool like SPICE, but instead of going back and forth in the iterative process, you will go to your simulation with an optimal design point because you already see the design space, you already pick the design point that matches your requirements, so that process becomes a systematic, optimized, and fast process. So there's a question about an open source version of ADT. So you can use a free version of ADT. I have a training on using the GM over ID design methodology and lookup tables. It's a free training for students. You can use this QR code to access the training, and it will also give you on a free version, give you access to a free version of ADT that you can use in your studies. So yes, you can access a free version of ADT. There is a question about using the tools with Virtuoso or other schematic editors. So the lookup table-based tools can work with netlists. So you can export your netlist from whatever schematic editor you are using, and then you can use the netlist with ADT or other lookup table-based tools. But of course, the good thing about using a tool like Virtuoso, for example, is that the integration can be much tighter and much better. Like, for example, here we have plugins for Virtuoso that you can use. So instead of going back and forth between two different tools, your schematic editor and your lookup table based tool, you can actually use your tool inside your schematic editor. So we provide integration, for example, for Virtuoso, and for other tools, you can also use them, but you need to do some processing, post-processing in your exported and imported data. So a question again about open source tool. So if you want an open source code, Professor Boris Merman already maintains a GitHub repository that actually contains some open source codes that you can use. But if you want to use a free tool, it is not open source, but you can use it for free if you are a student. Then you can also use ADT, which is included in this free training on the GM over ID methodology. So there's also a question about what range of error we can get between SPICE and ADT. It depends on the type of circuit. As I mentioned, if you do it the right way, you can get very small errors, like what I have shown in the case of band gap circuits. But in general, the error can be for the overall aspects of the circuit, like the bandwidth or the unity gain frequency or the phase margin and so on. The error can be in the range of few percentage points. So it depends on the circuit, but it can be something in the range of few percentage points. Less than 1% can also be done, but it is not the general case for every circuit. So there's a question about where are the differences coming from between ADT and the simulation results. One reason for the errors can be the finite step that you use to build the lookup tables. If your interpolation is not done in a smart way, so you can get some errors when you interpolate between the grid points of the lookup table. One more reason for the deviation is that when the lookup tables are built, like for example, let me go back here to this slide. When the lookup table is characterized, you sweep the three terminal voltages of the device, you sweep the device length, but you use a reference width. You use a reference width for the device, and you assume that the device properties scale linearly with the device width. And practically, the device properties can be actually sensitive to the device width due to narrow width effects. And in this case, you will see some deviations between the linearly scaled version, which you get from the lookup table, and the simulation result, which accounts for the narrow width effects of the devices. So this is one source of error. And you will also find, if you search my papers on Google Scholar, for example, you will find a paper that I co-published with Professor Merman on how to correct actually these narrow width effect errors by using auxiliary lookup tables. So this is actually a nice point of research that some people are working on in order to correct the lookup table errors for different device widths. So a question about post layout design considerations. So as I mentioned, if you use the black box characterization, yes, you can, for example, do a post layout view for your device, which includes the device and its parasitics. And then you can generate the lookup tables for this post layout view. And in this way, you will capture all the effective parameters of the device, including the layout parasitics. So the question about using ADT in the loop or building an API for ADT, a nice question, and this is something actually we are working on, and this is especially useful if you are using something like the AI agents and AI assistants, and you need some sort of API or terminal mode in order actually to integrate your tool in the AI flow. So this is yes something we are working on, and this will also make the ADT something that can you integrate in your AI-based design flow. So I think I have answered all the questions. If I missed your question, please post it again because I have come to the end of the list now. We still have 4 more minutes. So one question about the specs that cannot be directly computed from EC and DC results. In this case, you need to get your own expressions. As I mentioned, if your specs are coming from a transient simulation, like for example, you want to characterize the slew rate of your amplifier, or the settling time is easy actually. Settling time is a linear spec. It can be computed from linear analysis. But for example, the slewing behavior is nonlinear behavior, and this to get the slew rate, the actual slew rate, you need to run transient simulation. But the good thing is, if you analyze your circuit, and the AI assistant actually can help you in analyzing your circuit nowadays, you can get an expression for your slew rate. And the unique thing about using the lookup tables is that when you plug in numbers in this expression, like when if you want to plug in the capacitance, or if you want to plug in the bias current, you are not plugging in the hand analysis results. You are actually plugging in results from the lookup tables. So this is how the lookup tables can help you in nonlinear circuits. You will get the primitive values, like for example, the capacitance, the GM, the current from the lookup table, and then you will take these primitive values from the lookup tables and plug them into your own expression. So you avoid the simple analytical models errors, but you still need to figure out what is the equation that describes your spec in order to avoid running a full transient simulation to get it numerically. So yes, the recording will be available on the CAS website. I think, Dr. Chow, is it going to be sent to the attendees after the talk?
I think Samantha will release the link, right?
I'm sorry, can you repeat the question for me?
Yeah, about the recording link, is it going to be sent to the attendees after the
So
lecture?
the link in recording will be posted on the website once it's done processing, but it takes a couple days for the recording to process and be edited and then posted.
Okay, thank
But
you.
it will be available.
Okay,
Okay.
so thank you everyone again for being here, and thank you for the invitation. So Professor Chow, thank you very much.
Thank you, Hesham, and thank you everyone for joining the event, and have a nice day.
Thank you. Bye.
Bye.